Welcome to chapter 4.6. Here we will study the graphs of other trigonometric functions. So we've already covered the graph of sine of x and the graph of cosine of x. Let's start off now with the graphs of tangent of x and cotangent of x. Let's use our knowledge of the unit circle to help us in sketching the graph of the function y equals the tangent of x. Now remember, if we had our unit circle here, all right, starting at 0, we have 0. Up top, we have pi divided by 2. Over here on the left, we have pi, 3 pi over 2, and one complete revolution would be 2 pi. And if I asked you guys to evaluate the tangent of an angle theta on the unit circle, you would take the y-coordinate of a corresponding angle and divide by the x-coordinate, right? That's how we evaluate tangent. So if I asked you to evaluate the tangent of the angle 0, well, we'd find the angle 0, we'd take the y-coordinate, which is 0, divided by 1, the x-coordinate, and 0 divided by 1 is 0. Evaluating the tangent of 0 gives us out 0. Same thing must be true when we go to our function. If we plug in 0 for x, we have to get out 0 for y. Accordingly, I have this ordered pair 0, 0. Now, let's move to pi over 2. That's the same thing as 0.5 pi. If we evaluate the tangent of pi over 2, the y-coordinate is 1, the x-coordinate here is 0, 1 divided by 0 is undefined. Now, whenever these trig functions are undefined, they are going to generate a vertical asymptote. You might recall back to when we studied rational functions, whenever we had a fraction that gave us a non-zero divided by 0, we had a vertical asymptote. All right, so at pi over 2, evaluating the tangent of pi over 2, we have 1 divided by 0. That's undefined. Therefore, if I plug in pi over 2 for x into my tangent function, I have to get out an undefined value, generating this vertical asymptote. What about the tangent of pi? Well, evaluating the tangent of pi on the unit circle, we get 0. Therefore, if I plug in pi into my function, I have to get out 0. The tangent of 3 pi over 2. Again, y divided by x. That's negative 1 divided by 0, which is undefined. That's going to correspond to another vertical asymptote. And the tangent of 2 pi, well, that brings us right back to where we started. The tangent of 2 pi is going to be 0. Therefore, if I plug 2 pi into my function, I have to get out 0. We can also go in the opposite direction. The tangent of negative pi over 2. Well, that's the same terminating location as the angle 3 pi over 2. Tangent of negative pi over 2, well, that's going to be undefined, generating another vertical asymptote. Tangent of negative pi, that's going to be 0. The tangent of negative 3 pi over 2, undefined again. And the tangent of negative 2 pi is going to be 0. All right, so we've got a couple points on our graph, and we notice all of these vertical asymptotes. Let's try to figure out what's going to happen here in between each one of them. Well, values of x that are between 0 and pi over 2. Those correspond to angles in the first quadrant, right? The first quadrant is angles between 0 and pi over 2. And the tangent of every single angle in the first quadrant has to be positive. Therefore, the outputs of my tangent function have to be positive, meaning that as we approach this vertical asymptote, my graph is going to go up to positive infinity. Okay? It looks something like this. Now, what about between pi over 2 and pi? Well, on the unit circle, angles between pi over 2 and pi are corresponding to the second quadrant, and the outputs for tangent in the second quadrant have to be negative. Therefore, in this region here, all of my outputs have to be negative, and by definition of this vertical asymptote, as we approach the vertical asymptote from the right-hand side, our graph has to go down to negative infinity. Similarly, we could look at the region between pi and 3 pi over 2. Pi and 3 pi over 2 corresponds to the third quadrant on the unit circle. And tangent is actually positive in the third quadrant. That means that all of my outputs have to be positive, causing my graph to go up and approach positive infinity as x approaches 3 pi over 2. Hopefully you guys are beginning to see a pattern here, okay? As we go to fill in the rest of this graph, we get these nice curves, just like so, okay? And so there, let me get rid of these lines here. Here we have the graph of our tangent function. Y equals the tangent of x. Couple things to make note of. Our period. The period, again, refers to how long it takes the function to repeat itself. I can measure that from one midline crossing to the next, from one vertical asymptote to the next. The period of our tangent function is pi. Notice that's different from our sine and cosine functions. Our range, the range for our tangent function is all real numbers, negative infinity to infinity. And our domain, here's something to keep in mind. There are an infinite number of vertical asymptotes, okay? So our domain, the way we're going to write this, is all real numbers except we say x cannot equal, and we're going to pick one of the vertical asymptotes, and then add on n times however frequently they occur. All right, so we say domain, all real numbers, x cannot equal pi over 2, that's this first vertical asymptote that I see, plus n times how frequently they occur. And I have a vertical asymptote every period. And if the period is pi, I have n times pi. Okay, now there's a bunch of different ways you could write this domain. We could have also said all real numbers except x cannot equal, and pick a different vertical asymptote, 3 pi over 2. Okay, here I have another vertical asymptote, plus n times however frequently they occur. They occur every pi units. So you can pick whichever vertical asymptote you want. I will always pick either a vertical asymptote that lands on the y-axis, that would be 0, or I pick the very first positive vertical asymptote. Okay, so yes, this is not an incorrect answer, but my preference would be the one that I have written out. X does not equal pi over 2 plus n pi. Okay, let's look at our cotangent curve. Again, don't forget about our relationship to our unit circle. Here's my unit circle, 0, pi over 2, pi, 3 pi over 2, 2 pi. And if we're evaluating cotangent, well, on the unit circle, cotangent of theta, that's equal to x, the x-coordinate, divided by the y-coordinate. All right, so again, let's start off with 0. What is the cotangent of 0? Well, x would be 1, y would be 0. So that's undefined. Well, again, whenever these trig functions are undefined, what happens? We get a vertical asymptote, okay? So here I have a vertical asymptote at x equals 0. All right, let's go to pi over 2 now. All right, the cotangent of pi over 2. Well, to evaluate cotangent, we take x and divide by y. That is 0 divided by 1, which is 0. So if I plug in pi over 2 into my cotangent function, I have to get out 0. The cotangent of pi, that's negative 1 divided by 0, undefined, giving me a vertical asymptote here at x equals pi. The cotangent of 3 pi over 2, 0 divided by negative 1. Well, that's 0 again. And the cotangent of 2 pi, again, cotangent is x divided by y. That's 1 divided by 0, undefined. And hopefully you guys are beginning to see a pattern here. We could do the same thing going to the left from our y-axis. We'd have a 0, vertical asymptote, 0, vertical asymptote. Okay. All right, now let's try to figure out what our graph is going to look like. Here I am between x equals 0 and x equals pi over 2. That corresponds to the first quadrant on the unit circle. And what do we know about cotangent in the first quadrant? Well, it has to be positive. The outputs have to be positive. Therefore, the outputs of my function corresponding to this first quadrant, okay, first quadrant on the unit circle have to be positive, which means that as I approach this vertical asymptote from the right-hand side, my graph must go up to positive infinity. Okay, and As we move to the right, pi over 2 to pi. Well, on the unit circle, that corresponds to the second quadrant, angles in the second quadrant. And we know that cotangent must be negative in the second quadrant. All of my outputs for cotangent for angles in the second quadrant are going to be negative. Therefore, my outputs of this cotangent function have to be negative, which means as I approach this vertical asymptote, my graph must go down. All right. So there we have the shape of one period of our cotangent function. And again, notice all these functions, they repeat themselves. They are periodic. And so here we have the graph of y equals the cotangent of x. All right. Boom. So let's now talk about our period. How long does it take for this function to repeat itself? Well, it repeats itself every pi. The range of my cotangent function, all real numbers. Notice this goes up to positive infinity, down to negative infinity. And my domain. My domain is going to be all real numbers, comma, except x cannot equal. We pick a vertical asymptote. Notice we have one here at x equals 0, and we add on n times however frequently they occur. That would be 0 plus n times pi, or we just say x cannot equal n pi. All right, there we have our domain. Notice another acceptable domain would be all real numbers, except x cannot equal 2. Pick whichever vertical asymptote you like the most. Maybe you like pi. X cannot equal pi plus n times however frequently they occur. We have a vertical asymptote every period, therefore it occurs every pi. That would be another acceptable answer. All right, so there we have the graphs of our tangent and cotangent functions. In the next video, we'll talk about transforming these graphs.